Hi, everyone. So let me just make sure everything seems to be okay. If you look in the chat, I rebooted my computer this morning and like all my settings were off, but it seems that it's okay. And I mean, just let me know in the chat if you can't hear me. I mean, I guess you will because you'll see my lips moving, but not hear me. Um, Let me start then. Before I do any problems, today we're going to do two problems. One on center of mass, which is part of your assignment this week, and another one on the rotational kinematics, not the dynamics, because that'll be next week's topic. But I wanted to just say something about how I was going to run the class next semester. I was really hoping that we'd be past this whole COVID thing and we'd be back into a physical classroom. I so much prefer that over teaching this way. The information is the same, but just the delivery it's impersonal and it makes a difference, I think. And so uh, um, that's why I wanted to be back in the classroom. What I'm thinking of doing next semester is as you could see, the number of people in the chat right now are like six, which is pretty good. But that's like a small fraction of the class. I think it's half this class, and my other class hardly anyone shows up, and that's you know not the best because you can ask questions when we're in the live chat, but I can understand that because people can always watch it later. Okay, so the live chats didn't work out quite as well as I thought. So next semester, I was thinking of actually doing 3 hours of pre-recorded lectures and replacing the live chats with physical in classroom time. Okay, now that's optional. It'll probably be in the evening, something like 6 to 9 Tuesday evening or something like that. I haven't decided yet, so don't quote me on that. But basically, replace this live chat with an actual like pre-recorded lecture, okay, where you would not be able to ask questions, but then have like the equivalent of asking questions in a physical classroom, so we could actually like be together. It would be optional, so you don't have to do that, but I think that would make it a little bit more personal. Okay. Now, this isn't written in stone. I'm probably going to send out an email next week specifying what the changes are and see how people feel about it. Some people might say, yeah, great. I kind of like the pre recorded lectures because then you can watch them at any time you like. And I don't really have that many questions. I know what I'm doing. I do well on the tests. And so, that's fine. But other people are going to say, well, we want to ask questions. And I was thinking we would do that in person. Okay. And you we would show up and you could ask me questions if you had questions, and if you don't have questions you could still show up and I could just produce questions like I do during the live chats. I'll say, hey, here's a question that we can do together, and we could do that. Okay, and that would be one change. The other change is a little bit different. It's not really a matter of the delivery. It has to do with logistics. It's something I've discovered this semester. When you set a syllabus at the beginning, you kind of have to follow it because people make decisions about it. And like if you miss a test, that was it. And it's not to be, overly strict. I had to follow the rules because other people are following those rules, and some people did. And there's nothing I can do for non-emergency reasons. Okay, so what I was thinking next semester is to change that rule slightly and say, look, if you miss a test, you could do it the next day and you would lose 10%. For every day that you miss it, that you're late, 10% off. But then we can't go too long because eventually I got to make the test available or the results of the test available to the entire class. So something to that effect that just sort of softens that deadline. But these emails that I send every morning, I hope they're not that annoying, and that they're repetitive, and that's on purpose so that no one can say, look, I didn't get that message that this was happening. But on a with an internet course like this, a lot of people can become quite disconnected and they can kind of walk away from it for a while, and then they come back to it and say, oh, I would better do something, and go, well, whoa, we missed this test. And so I'm trying to think of ways around this. Again, none of these things would be problems if we were physically in a classroom, but it looks like things are still going to be problematic even next semester. And the rules just changed again. I don't even know because I don't teach any classes on campus, even though I'm like 2 blocks away from campus and within walking distance of campus from my house. And yet, I'm in this weird situation. So anyhow, this is for your thought. If you have any feelings about this, you go, no, I love the course the way it is, leave it alone. Feel free to email me or whatever. Like I said, I'll specify it very clearly in an email that I'll send out next week. And, however you feel, because you guys experience this course from your end and I'm experiencing it from my end. And, I don't know, like, I don't get the same kind of feedback that I do when I'm with people, directly in a classroom in real life. And so I just felt that I thought I better, open it up to these possible changes. I'm suggesting things, but there it is. Okay, so let me just see in the chat if anyone's has anything to say about that. Okay, well, no one's really responding right now, and you don't have to respond right now, but think about it. Okay, so once again, it'd be all pre-recorded lectures online. Okay, and still problem solving like this, but in a pre-recorded fashion, and then direct questions that you can ask me during an evening session which would be on campus, and you would have to wear masks and follow all the rules, but something like that. And that would be optional. That evening one would be optional. Okay. You could always ask me questions by email. You can also always ask me questions on Google Hangouts for those evenings, which I will be able to do it. It won't be every week like I can this week, but for those days, evenings when I can be available, I will be. And there it is. The other difference with Physics 102 next semester is the subjects are a little different. This semester, really there was only 5 topics we covered. I know that sounds strange. It seems like we covered a lot of material, but each one of the topics are very deep. Next semester is more isolated topics, and so a lot of the problem solving you don't have to go through all the steps. Like especially the Newton's laws problems had a lot of steps to them. Okay, and you really had to see how that was done. But some of the problems next semester are pretty cut and dry, and so you don't really need as much of this as long as you watch the pre-recorded lectures in which I do solve problems. You don't need so many extra problems. They're all pretty similar. Okay, so it's slightly different that way. Okay. Anyhow, there it is. Let's. I don't want to waste too much of your time. Let's just do some problems. Okay. So the first problem we're going to do is a center of mass problem, and I purposely didn't do a diagram here. I've got a diagram. I'll show it to you after we finish the problem. But when you do these center of mass problems, like on the assignment, if you've done it already or you will do it, you'll see that I drew a kind of an ASCII diagram to show you where everything was in 2D. But you don't really need that. All you need is just the information. These problems are pretty straightforward. And what they are is basically what a center of mass is. It's basically a weighted average. Okay. And so here I say find the center of mass of the following system of masses at the given locations. Okay. And so I have a 3 kilogram mass at x is equal to negative 1.3 meters and y is equal to 1.4 meters and so on. Okay. And we say, okay, where's the center of mass of these four masses here. Okay. And you could sketch the diagram, and like I said at the end, just to get some intuition, we will, but you don't need that. It's easy enough to just calculate it directly from the numbers. So you calculate first the x component, because the center of mass is a vector. Okay. And if you're in 2D, so you've got an x and y component, so you calculate the x component of the center of mass, and then independently calculate the y component. Okay, so just like any Cartesian, the x and y completely decouple. Okay, and the formula for that is this formula right here. Okay, and the way I wrote it there, I have the ellipses in there, the dot dot dot. It just means you would just, if you add more masses, we only have 4, but if you have more masses, you just add more and more and more. So in the numerator here, you have like mx for each of the masses. So m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 plus m5 x5 if we had an m5, and so on. Okay, so it's basically mass times its x coordinate, all right, divided by the sum of all the masses. Okay, so m1 plus m2 plus m3 and all the rest. Okay, in our case there's only one more, m4. Okay, and this is actually a weighted average. So if you've done statistics, that's exactly what how you do a weighted average in statistics. Basically what you're doing is you're saying, oh, some of these x values have more weight than others. The bigger the mass, the more it tends to draw the center of mass towards it. And you'll see that at the end, okay, when I show you the diagram. Okay, so it's just a matter of substituting in. For M1, that's like 3 kilograms, and its x value is negative 1.3. There it is. Okay, M2 is 4 kilograms, and its x value is 0.95. M3 is 5 kilograms, and its x value is 2.05. Okay, and here's M4. And there's its x value, okay? Divided by m1 plus m2 plus m3 plus m4, in other words, 3 plus 4 plus 5 plus 1, and that works out to positive 0.742 meters, okay? So next we do the y, and here it is. Here's the equation for y. It's exactly like the x, except instead of x values, you replace them with the y values, okay, the y components. And the next line is not a typo. All I did was I took out the previous line, and I just removed the x values there like that, just to show you that the x and the y have exactly the same structure. All you're doing is replacing x1 by the y1 value. Okay, so in here where x1 was, you're going to put the y value, y1, and that's 1.4. So over here, that's that y value there like that. Okay, and then over here you put the y2 value, and that's that value right there, and it turns out to be negative 0.135. All right, very easy. You didn't need the diagram. You don't even have to picture it in your head. These are that straightforward. But let's look at a diagram of where these points are. So this diagram here shows, oh, that's weird. Um, Okay, it should be fine. It's a little bit skewed, but we can live with it. Again, one of my settings was off, but that's okay. We can work with it. So here are the four masses, and I've drawn them at their x and y coordinates. And where's the x value? Well, sorry, the center of mass. Its x value we found to be 0.742. So I'll do this in blue, positive 0.742. So if you go over here, this is 0. Okay, that first tick, that's like 1. And 0.74 would be somewhere around there like that. And so the center of mass has to be somewhere along this. I'm doing a terrible job there. One sec. Okay, let's try that again. There we go. Okay, so it's somewhere along there. And the y value turned out to be negative 0.135, so it's somewhere like around there. I'm just estimating, okay, like that. And there it is. That's where the center of mass would be, okay? So you can see that it's not in the geometrical center of these 4 points. It's actually slightly closer to the 5 and the 4 kilogram mass. And that's because it's, again, a weighted average, and so the 5 kilogram mass tends to pull it towards it, and the 4 kilogram mass tends to pull it towards it. Not so much the 1 kilogram, and not so much the 3, a little bit less, and so the 4 and the 5 tend to dominate it, okay? And it's I wouldn't say it's in the middle of the 4 and the 5, but it's being pulled pretty much the same by both, a little bit more by the 5, obviously. Okay, so yeah, it kind of makes sense. If you were to draw a perimeter here like this, like that, like that, like that, that's a terrible perimeter, but okay. The center of mass has to be within that perimeter. It could not be, you could not have a center of mass out here. Why? Well, because, if you did, that means that there would have to be some mass on the other side of it, because these masses would tend to pull it this way, and so there'd have to be another mass on the other side of it to pull it out, to pull it that in the other direction, this way towards it, and there isn't such a mass, okay, and so it can't be outside of that perimeter. So just as a check, you say, okay, where did I find the center of mass? It has to be within this kind of a box that or quadrilateral that joins the points. Okay, so there we go. Let me just clean this up quickly and actually take that all out of there. All right, so there's our first problem. Okay, let's see if there's any questions about that. People seem to be okay with that. I'm not seeing any questions in the chat. All right. Let's go on to our next problem. So our next problem is a problem to do with rotational kinematics. Okay, so when I did the pre-recorded lectures before the semester even began, I didn't know quite where we would end up. In retrospect, I should have split it. I should have split it, with the rotational kinematics on one and rotational dynamics on another. I didn't. But for this week's, we'll just do the rotational kinematics. Next week, you can finish watching that video, and we'll do the rotational dynamics. Rotational kinematics is exactly that, a description, mathematical description of the motion, rotational motion. Okay, and usually this comes after center of mass because previous to this point in the course, we treated all masses as if they were all objects as if they were point masses. Okay, we never really worried about their extension. If you remember when we did the Newton's law problems, we had these forces acting on blocks on inclined planes and stuff like that, and we always attached all the forces at the middle, and we said, well, don't worry about the fact that this is an extended block. We'll just pretend that all the forces are acting in the middle. Well, that middle now we know is the center of mass. Okay, so we just pretend like all the forces are acting at the center of mass, and the motion, excuse me, the motion of an object can be described as the motion of the center of mass and then the motion around the center of mass. So if I take an object like, here's my remote, okay, and I throw this remote in the air, which I can't do. In a physical classroom, I do this with the eraser. You watch it, and what you see is that, the center of this thing, the center of mass of this thing, follows a parabola, but it rotates as it follows that parabola. So, when we talked about that parabolic motion earlier in the course is as trajectory motion in 2D under constant acceleration, okay, we said it follows a parabola. Really what we should have said is the center of mass follows a parabola and the rest of it rotates, okay? And so now the remainder of the kinematics is describing that rotation, okay? Now if something is freely rotating, it'll rotate around an axis through the center of mass, okay? But I can always force it to rotate around some other axis, like, the center of mass is somewhere in the middle here. Okay, it's actually where it balances, and I'll show you why next semester. That's one of our first topics next semester is statics. I can't get this to balance, but you got the idea. All right. Sorry, but I can always force it to rotate around one of the endpoints just by grabbing it there and forcing it to rotate around that endpoint like that, okay? And so, rotational motion is usually around the center of mass, but it could be any rotational motion you like. Okay, so having said that, let's do a centrifuge. I think in the pre-recorded lecture I did a disc, like one of those old LPs. Here I just looked on Amazon.com and I looked up a centrifuge. And if you've done any biology or in chemistry, they use centrifuges, which are you put these test tubes in this thing and it spins really fast. Okay, and what it does is if it's blood, it'll separate the blood into the various different layers. Okay, so like the red blood cells will go to the end, and then the plasma will come up towards the top. Okay, so it basically separates out the blood, and you could do it with milk and all other kinds of stuff like that. Okay, and that's by just creating artificial gravity, if you like a really big acceleration. Okay, and these things are called centrifuges. All right, so I just looked this up, and all the numbers I have in here are actually correct, except that 45 seconds. I don't know how long it takes to spin up, but all the other numbers are actually real numbers. Okay, for a real centrifuge I looked up. I should have probably got the link here, but it's okay. So a centrifuge starts from rest and spins up to 5,000 RPM. RPM is revolutions per minute, okay, in 45 seconds, okay? So I put my test tubes in there. I close the top. As a safety feature, I have to close the top because it spins very fast, okay? And you turn it on. And it starts from rest, and then it spins faster, 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 until it spins up to 5,000 RPM, and then that's it. That's the maximum it gets to, okay? The bottom of a test tube experiences an acceleration of 3,740 Gs, okay? Now, G is the acceleration due to gravity, 9.8 meters per second squared. We'll round it off to 10, as we usually do, okay? So, you'll often see large accelerations written in, not in terms of meters per second squared, but in terms of Gs. And that just means times the acceleration due to gravity, okay? When it's at its maximum speed, when it's spinning at its maximum, okay? All right, so that's the bottom of the test tubes, and that's the part of the test tube that's furthest from the axis, okay? And assume constant acceleration, okay? I don't know if that's true or not, but it's pretty safe assumption. Okay, so you got the picture. You've got these test tubes that are sitting. They kind of sit. You kind of put them in at an angle. Okay, and then they spin. And at the bottom of the test tube is a certain distance from the sorry. This is the axis. The bottom of the test tube is a certain distance from the axis, and they're going to spin. And that bottom of the test tube experiences quite a bit of acceleration. Okay, the first question is, what's the angular acceleration? Okay. Second question is, how many times does the centrifuge turn during the first 45 seconds as it spins up, okay? And what is the centripetal acceleration at maximum speed, okay? And how far is the bottom of the test tube from the axis, okay? So that's the part of the test tube which is furthest from the axis that experiences the most acceleration, all right? And how fast is a point at the bottom of the test tube moving at maximum speed, all right? So let's answer the first question. All right. So what is the angular acceleration? All right. Now there are three equations here. Here they are. Okay, and these equations should look familiar because they're exactly like the 1D kinematic equations, but for rotational motion rather than linear motion. There we had x, v, and a. Here we have theta, omega, and alpha. Okay, and theta is the angle, omega is the angular velocity, and alpha is the angular acceleration. All right, so the first equation is written a little bit differently than you might have seen it. Basically, I wrote delta theta here like that. You might have seen this written like this. I'll just write it very quickly so that you could see the way like that. Okay, so just look at that right there. All right, and basically you start at some angle theta naught, and with some initial angular velocity omega naught and some angular acceleration alpha, and then after some time t, you're at angle theta. Okay, the thing is that usually at t equals 0, we don't say we start at any old angle, we say we start at 0 angle. So this is not as interesting as just like subtracting theta naught from both sides and thinking of this side here as not an angle, but as a change in an angle, like how much, through what angle did this thing turn, okay? And we just call that delta theta, like that, okay? So the only reason I showed you that is that, this is the same equation that you've seen before, but you go, well, where's that plus theta not there? Well, I've just incorporated that into the delta theta, okay? It's maybe a better way to think about it, okay? And then equation number 2 is if you start at some angular velocity omega naught and you have angular acceleration alpha, you wait a time t, you're at some new angular velocity omega. Okay, and then the last one, omega squared is equal to omega naught squared plus 2 alpha delta t, is just equations 1 and 2 with time eliminated. All right, so let's go through this. Let's see what we know. Okay, so if we look back up here, I say the centrifuge starts from rest. Okay, what does that mean? Centrifuge starts from rest. So if it's not moving initially, that means its angular velocity is 0. Okay, so just like a car that's not moving, car's going to go straight down a road, 1D motion. Car's not moving, V naught is equal to 0. Here, it's not spinning, it's not turning at all, omega naught is equal to 0. That's like before I throw the switch, okay? I throw the switch, wait 45 seconds, it spins up to, well, it says it spins up to 5,000 RPM. So the final angular velocity is 5,000 RPM. Okay, again, this is like that record player example I gave. All right, there's a bit of a difference, which we'll see in a bit. Okay, now RPM means revolutions per minute. Okay, and that's not MKS. All right, and revolution is just synonymous for turn. Okay, so you say, well, okay, if I want to convert from revolutions, I need to go to radians. How many radians are in a turn? There's 2 pi radians and 1 revolution. Okay, and that's this conversion fraction there. Okay. Now the way I wrote the reason I wrote it this way is because revolution here is in the numerator, so I want revolution here in the denominator. Okay, and that'll convert from revolution to radians. Okay, and then the other one is minutes to seconds because we want it in radians per second. Okay, so minutes in the denominator, you want minutes in the numerator. 1 minute divided by 60 seconds is 1. So there's that conversion factor. Fraction, sorry, and that gives you 523.6 radians per second. Okay, generally speaking, if you just want to know if you got it right, if you've got it in revolutions per minute, roughly divide by 10, and that's the answer you should get in radians per second. Not quite; it's a little bit off, but just so you in your mind, you go, well, what number should I expect? I've got 5,000 revolutions per minute. What should I expect? Somewhere in the neighborhood of 500, 1/10 of it. Okay. Okay, and it actually turns out to be 523.6 radians per second. All right, so we know that. What else do we know? Well, the next thing I said is that it takes 45 seconds to spin up. Okay, and what do you want to find? Well, I'm asking for the angular acceleration. That's alpha. So you want to find alpha? Well, you look through the equations and you realize you can't use number 1. Here, let's look at them again. You can't use number 1 because you don't know delta theta. Okay, you can't use number 2 because you don't know delta theta, and again, you want to find alpha. Okay, so there's 2 unknowns here. There's 2 unknowns there. Okay, this is the only one where alpha is the only unknown. Okay, so you want to use equation number 2. There it is. All right, substituting in, there's your final angular velocity. There's the time. And there's your initial angular velocity, and that gives you 11.6 radians per second. Okay, so fairly easy, especially since we've done a lot of 1D kinematic problems. At this point, this is pretty much the same. It's just you have to think angularly. Okay, all right. How many times does it turn during the startup time of 45 seconds? Okay, so it starts from rest. And it starts to turn, and then it turns faster and faster and faster. I would just want to know how many times it actually turned in that 45 seconds. Now, you might wonder, geez, how do I do that? The word turn, like how many turns does it make? A turn is an angle. And that sounds kind of strange to say a turn is an angle or an angle is a turn. You go, well, how do I think about that? When I say a turn, you think of this. When you think of an angle, you might think of like a wedge, like what's that angle between that wedge? But, a turn is an angle, okay? You might say a quarter of a turn. What's a quarter of a turn? Well, that's 90 degrees if we were working in degrees, okay? So a quarter of a turn is 90 degrees. Half a turn is 180 degrees, okay? An eighth of a turn would be 45 degrees. Okay, so like a fraction of a turn turns out to be some angle, all right? A full turn is 360 degrees. 2 turns would be twice 360 degrees and so on. Now, I did it in degrees because most people are familiar, but same thing with radians, okay? So you say a quarter of a turn, that's pi divided by 2 radians, okay? Half a turn, that would be pi radians, and so on, okay? So whenever you see a question in rotational motion that says how many turns or how much of a turn or anything to do with turn, think theta, think angle, okay? So this question is really asking for that delta theta, okay, which is why I wrote it in terms of delta theta. It's like how much of a turn, how much of an angle, how much does the angle change, okay? So delta theta, all right? And again, don't think of the angle as having to be, confined to less than 1 turn. It could be many turns, in which case the angle is going to be much greater than just 2 pi. All right. So let's calculate delta theta, and we can now because we have all the other quantities. We could actually use equation 3. I'm using equation number 1 here, but you could use equation number 3 because now we have alpha. Once we have alpha, we could calculate delta theta using either equation 1 or 3. I use number 1 because it seems more obvious. It has delta theta already isolated. And so, a half times alpha times t squared plus omega t, substituting in the numbers. Now for alpha, we didn't know it before, but now we do because we just found it, right here. Okay, and that turns out to be, that gives the answer of 11,745 radians. Okay, that's what comes out. Then what? Well, maybe, when you look at my answers, because, multiple choice, you look at them and you see that all my answers in radians, well, then you should see an answer there of 11,745 radians, and that would be the right answer. But maybe you don't. Maybe you see turns, okay, or revolutions, in which case you got to convert, okay? And since the question asks how many turns, let's convert it back to turns. And to do that, you just convert to revolutions. A revolution or turn, totally synonymous, okay? So, here we have radians. We want to convert to revolutions. So what we do is we multiply by that conversion fraction, which is 1 revolution is equal to 2 pi radians. So 1 revolution divided by 2 pi radians, that's 1. You can always multiply by 1, and that gives you 1,869.3 revolutions. Okay, that's the answer. That's how many times this thing would turn in 45 seconds. 45 seconds isn't that long, and this is close to 2,000 turns. I mean, that's quite a bit, okay, because this thing is really spinning. All right, so there you go. There's that question. Okay, let me see if there's any questions in the chat here. All right, 5 people viewing, and I don't see any questions. I agree this is pretty straightforward stuff, but in case anyone has questions, I want to make sure we're all good with this. Okay, so what's the centripetal acceleration at maximum speed? Well, this is I wouldn't say it's a trick question, but I can see how students might get tricked. They'll go, oh, I got to find an equation that has that gives me centripetal acceleration. Not really. I give it to you in the problem. Let's read the problem again, and you'll see that information is there. Slightly indirectly, but still there. The bottom of the test tube experiences an acceleration of 3,074 g. Okay, so I didn't say it was a centripetal acceleration, but it is. Okay, so all the stuff that we did with uniform circular motion earlier, that still applies here. Rotational motion is more general than uniform circular motion because uniform circular motion is rotational motion with alpha equal to 0. That's all it is. Okay, it's just a constant omega. Omega doesn't increase, omega doesn't decrease. That's why we're uniform, and so it's just alpha equals 0. Okay, here we allow any possible alpha. All right, and so this is more general. Okay, but once this thing is spun up to maximum speed, it doesn't keep increasing. It doesn't go past that 5,000 RPM. In that case, after the 45 seconds, alpha is effectively 0, and you're back to just uniform circular motion. And there's a centripetal acceleration. What is that? That's the acceleration to the middle. Because why? Centripetal means towards the middle. Why? Because things want to go in a straight line, but you're making a turn, And so there has to be an acceleration which keeps it on the circle. That's the centripetal acceleration, and that's what that 3074 G is. Okay, now we needed an MKS, we needed in meters per second. So down here, we just take the 3074 and G we write as 10 meters per second, and there it is. Okay, if you wanted it more accurately, multiply it by 9.8, but there it is. So basically you're looking at an acceleration of 30,000 and some change meters per second squared. This is huge. It's absolutely astronomical. I mean, it's beyond anything that you would have. It's even more than the gravity at the surface of the sun. Okay, so these centrifuges can produce quite a bit of a acceleration. You might call it artificial gravity. Okay, and so yeah, it's like 3,000. It's like an object in there weighs 3,000 times more than it would, just at the surface of the Earth. Okay, so human beings can handle maybe 7 to 9 Gs before we pass out, and it's not at all pleasant. Okay, like 3 Gs might be okay for fun if you're like in a carnival ride or something. You'd have to be in a very fast jet, like a fighter jet or something like that, to get 7 to 9 Gs. But then you couldn't experience it for very long, otherwise you'd pass out. I mean, basically all the blood goes to one side of your body. So 3,000 Gs is just crazy. I mean, I pity any bacteria or cells that might be in there. They'd be crushed. Okay, anyhow, there it is. That's the centripetal acceleration, and we've been given that. We've given it that the symbol A subscript C. Okay, so AC. So there's the centripetal acceleration. Now here it says how far from the bottom of the test tube, how far is the bottom of the test tube from the axis? Okay, so when these test tubes sit in there, there's the bottom, and the bottom is going to sit as far from the axis as possible. That's the middle that it's spinning around. And the reason is that that's where you want the most acceleration. Okay, and you say, well, is there a relationship between stuff that we did above and that radius? And yeah, there is. When you have angular quantities like alpha, omega, or theta, and you have linear quantities like v or a, they're related to one another by a factor r, or r squared. Okay, and so there's two equations for acceleration. Here, there's the equation for the centripetal acceleration, which is the one we want in this problem, and then there's an equation for the tangential acceleration. So the centripetal, because this thing is going on a circle, the centripetal acceleration is the acceleration into the middle, but because it might be speeding up or slowing down, in this case it's speeding up as it turns. Okay, there's also a tangential acceleration. Well, it turns out that the tangential acceleration is very small. Okay, and even if you look at that tangential acceleration during that first 45 seconds as it speeds up, it's tiny compared to the centripetal acceleration. The centrifuge depends on that centripetal acceleration to give you the the effect of artificial gravity of separating out the liquid or the colloidal solution or whatever. Okay, so so we're going to use this one right here, and so starting from that, I just rearranged that. I divided omega squared, both sides by omega squared. So that gives me an AC here like that. And omega squared on the bottom there like that. Now we have omega. It's that 523.6 that we calculated above. And that gives us 0.11213 meters, or rounding off to three significant figures, 11.2 centimeters. I actually looked if I could see, the size of this thing. I didn't, but that is totally reasonable. If anyone's ever worked with these centrifuges, you know that the test tubes, when they sit in there, their bottom, the furthest point from the axis, is about 10 centimeters. Okay, so this makes sense. So if you got an answer which was like 2 meters or 10 meters or something like that, that's crazy, because these things are not that big. And so 11 centimeters is a very reasonable number. Okay, so there you go. That's how far the bottom of the test tubes are from the axis. Okay, now I didn't ask for the tangential, but I said, you know what, let's calculate it. Now, not after it's spun up, but while it's spinning up, there is a tangential acceleration, and that's given by this other formula, r times alpha. Okay, and r is equal to, well, we just found that right here. Okay, and alpha we found above. Okay, and it turns out to be only 1.3 meters per second squared. Well, compared to the 30,000 meters per second squared to the 1 meter per sec, 1 meter per second squared. Okay, 1.3. But obviously the tangential is tiny. It's absolutely tiny. Okay, and this is very typical of these circular motion or rotational motion problems. All right, last question, and then we're done. How fast is a point at the bottom of the test tube moving at maximum speed? In other words, I want to know the tangential velocity. Like, if you were there and you were like actually seeing how fast are you moving on that circle, well, that's your tangential velocity. Okay, and that's given by this equation. Okay, so velocity is a linear quantity. Omega is the angular velocity, it's angular equivalent. Okay, and how do you relate the linear to the angular? Multiply by r. Okay, same thing here. Here's the linear, here's the angular. How do you relate them? Multiply by r. Okay, so the tangential velocity is equal to r omega. Substitute in for r and omega that we have from above, and we find that the test tubes are moving at the bottom, at least, are moving at 58.7 meters per second. Okay, that's really fast. I didn't ask for it in kilometers per hour, but that's like over 200 kilometers per hour. What would that be? I guess that would be somewhere like 120, 130 miles per hour, something like that. Okay, so that's pretty fast. Okay, and you don't want to be hit by something that's going at 130 miles per hour. Okay, so in order for the centrifuge to work, you have to close the lid, and the spinning is inside of that, and that's a safety feature because you really don't want to put your fingers in there when it's spinning. Okay, and so that answers that question. All right, that's it for today. Next week, like I said, we'll do the dynamics, and that's it for the topics of the course. There's that break there with Thanksgiving, and then when we come back, it's the last week of classes, and we're just going to review for the test, okay, which will be on the Friday of the last week of classes. I think, don't quote me on this, I think that's the December 4th, okay? It's in the syllabus, okay, and we have to follow the syllabus, okay? But I seem to recall that it's December 4th. Okay, is everyone okay then with what I've done so far? Do you have any questions, or are we good to go? Let me actually type that in the chat. Is everyone okay? Any questions, or can we end the stream? All right, I'll just wait a few seconds because there is a bit of a delay. All right, good. Thanks, Emily. All right, you know what? We're good. I mean, I think you guys are pretty good. I'm sure you understand this stuff. It's fairly straightforward. All right, let me end the stream.